Hi, my name is Aaron Sampson. When personal computers first hit the scene in the late 1970s, they were certainly very useful, but it was the advent of the internet and other technologies that really began to change the world of computing. In this course, I'll explore the basics of current internet connection technologies and various types of computer storage. Then I'll examine the various computer types in use these days, including mobile devices and even gaming systems. Finally, I'll cover a relatively new branch of computing known as the Internet of Things, or IoT. Upon completion, you'll have built a foundation for the basics of IT. This course helps to prepare learners for the CompTIA IT Fundamentals, or ITF Plus certification exam, FC0 U61. In this presentation, we'll take a look at accessing the Internet using fiber optic connections, which quite literally refers to the fiber optic cables that are used and the method by which data is transmitted, which is to use small pulses of light from a laser to represent the digital ones and zeros traversing the cable, as opposed to electric signals running over a copper wire. Now, there are several characteristics that make fiber optic the better choice for internet access, which we'll come to in just a moment, but as of the time of this recording, it certainly hasn't replaced copper wires just yet. Most large-scale providers in developed areas have implemented fiber as their backbone, but copper has been the infrastructure of choice for decades, so for more rural areas with less developed infrastructure, you would most certainly still find copper being used, and it's only relatively recently that fiber optic has become economically feasible. So if an infrastructure upgrade is happening in any given area, then fiber would likely be replacing copper. As for some of its characteristics, because it literally uses pulses of light, the signals are far less prone to interference. Electrical signals on a copper wire can become distorted if they pass too closely to a strong magnetic source or other power source or even strong radio transmissions. But light is virtually immune to all of those detriments. And when using copper, the wire itself acts as a source of friction, so the signals degrade more and more the farther they travel. And this is referred to as attenuation. And as the signals become weaker, they're even more susceptible to distortion. So standard Ethernet cables, to this day, are limited to spanning a distance of only about 100 meters. Now, that's in a LAN implementation, but that's still the limit of an Ethernet cable. Other methods of high-speed internet access still use copper cables, but the primary run from the provider to your home is not using Ethernet. But we'll come to those other methods in an upcoming video. But since fiber optic uses light, its signals can travel significantly farther before any noticeable degradation occurs, typically measured in kilometers or miles as opposed to meters. As for the physical infrastructure itself, the actual cable has a core made out of extremely thin glass filaments that are barely thicker than a human hair, but they're surrounded with many protective and reflective layers that can keep the light pulses moving forward even when the cable is not run in a straight line. And the physical layout from the provider will certainly involve a fiber optic backbone that represents the main line of the provider, then a portion that is actually run into your home, which itself might still be Ethernet, or it could be fiber optic right to your specific receiving device. Now, while it is usually nowhere near this long, that last section that is run to your home is generally referred to as the last mile, but as far as you and I are concerned, it's simply what type of connection branches off the main line and runs into the home. A pure fiber connection refers to one that is using fiber optics all the way into your home, which would be the fastest option, but as you might imagine, it's also more expensive. So if budget is a concern, an Ethernet run over the last mile would sacrifice a little bit of speed, but it would be less expensive and possibly more compatible in that you might not need to replace your primary access point. As for some of its advantages, most providers offer speeds of at least 1 gigabit per second, many offering 1.5 or even 3 or higher, which significantly outperforms DSL internet and most implementations of cable. It has a very low latency or lag time as compared to copper, again because the copper wire itself acts as a drag, so to speak, on the signal, and that just doesn't happen with pulses of light. The signals do have to do a lot of reflecting, which does slow them down, of course, but overall fiber optic has a lower lag time than any copper medium, and because of its lower susceptibility to interference, events such as lightning or solar bursts don't affect fiber optic, resulting in fewer outages. Those advantages translate into several practical reasons to go with fiber optic as your internet connection method, include both fast uploads and downloads. Most cable and DSL connections dedicate most of their bandwidth to downloads because that's what most of us want from our connections. For example, streaming a movie is a download. But for operations such as transferring data to the cloud, for instance, for backing up important personal documents, that's an upload. So faster upload speeds are important to many users as well. If you are commonly streaming high-definition video, then fiber will provide a much smoother viewing experience, or if you're downloading it to watch later, a full-length feature film might download in a few minutes as opposed to hours. And coming back to the imbalance between upload and download speeds, on most cable and DSL connections, for applications such as video conferencing and online gaming, you're sending just about as much data as you're receiving. So the balance in bandwidth as far as bidirectional traffic goes needs to be more or less 50-50, whereas cable and DSL tend to be configured for about 85-15 in favor of downloads. In short, if fiber optic connections are available in your area and it fits into your budget, then there would really be no reason that you shouldn't choose it. It definitely provides the highest level of performance across the board as far as internet access is concerned. In this presentation, we'll provide an overview of the internet access methods that still use copper wires as the primary transmission media, including DSL, which stands for Digital Subscriber Line, and cable, which refers to the cable that provides cable TV service. So, beginning with DSL, this method uses the copper telephone lines that still exist in almost every location that has phone service. But since it uses digital signals instead of analog, it requires a DSL modem to be installed, which is used to modulate and demodulate digital signals so that they can be transmitted over a traditionally analog medium. Now, one of the biggest advantages of DSL right out of the gate, so to speak, is the fact that it does use the existing infrastructure of the telephone network. So it's available almost everywhere, including very rural or remote areas. As for the speeds that were supported by DSL, it would typically vary based on the provider, and many would offer different packages, so different speeds would be available for different prices. But the faster plans would usually accommodate speeds of up to or around 100 megabits per second. Now, just as a reference, that's significantly slower than the current speeds supported by fiber optic, but it would still be sufficient for activities such as video streaming and even online gaming, but there are some caveats. Most notably, the speed that you might actually receive to your home is dependent on your distance from the nearest transmission station of the provider. Recall that DSL still uses copper wires, so the greater the distance that has to be traversed, the more degraded the performance will be. And DSL also tends to suffer a bit more as more users are making use of the same connection. But to be fair, that really happens with all network connections, but its lower bandwidth overall tends to make it a more noticeable effect. Some overall pros and cons of DSL then include a generally adequate service for most uses, but again, that is dependent on what your uses are. If you have a home full of gamers and video streamers, then it would likely not be adequate. But if you just generally browse the internet, use email, and even stream content periodically, it would likely suffice, and in that event, it can offer a lower cost solution. And again, because it uses existing phone service lines, it's one of the most widely available options. Performance will also generally be adequate if there are fewer users making use of the connection at the same time. Cable internet is generally much faster than DSL, at least these days, and I'll come back to that point in just a moment. And again, the name refers to the use of the same type of coaxial cable that has provided cable TV services to many of us in the past. So the reason I say at least these days is because in the earlier implementations of both DSL and cable, there were many packages on either platform that offered comparable speeds. Now, all of which would be effectively obsolete by today's standards, but early cable connections were not as fast as they are today. So again, in those early years of high-speed internet, you might have been able to get, let's say, a 25 or a 50 megabit per second connection from either cable or DSL, but ultimately the coaxial cable used with cable internet inherently supports greater bandwidth than phone cable, so cable internet speeds available today, in fact, can be comparable to that of fiber, but because it still uses a copper wire medium, it still suffers from signal interference, degradation, and distance limitations more so than copper. Now that said, like DSL, most providers will still offer varying packages with different prices for different speeds, so you can save some money if you feel that you don't need the highest speed, but current cable providers will generally offer speeds of up to 1 gigabit per second, which again, for pure bandwidth, is comparable to fiber optic. But most fiber optic packages will offer at least 1 gigabit per second, then there are usually packages above that. So, some overall pros and cons of cable include reliability due to the more robust nature of the cable itself. It has a single copper wire core that is much thicker than the wires inside phone cables, so it's much less prone to damage, and like DSL, cable TV service has been widely available for a very long time, so it's also more available in rural or remote areas, at least compared to fiber. But it can also suffer more with a higher volume of use, but in a different manner than DSL. Cable performance degrades with what's referred to as higher community use, meaning that the more users there are in a particular region, such as a neighborhood or a few blocks, because a single service is delivered to that area, then split, so to speak, among all subscribers in that area. So the more people there are in your neighborhood using that same service at the same time, the lower the performance. That kind of community degradation doesn't happen with DSL because each subscriber has a direct phone line connection from the provider into their home. But again, recall that multiple people in the same home, all using that connection at the same time, will still cause a decrease in performance. But in your home, you might only be sharing the connection with one or two others. With cable, you could be sharing it with hundreds. But again, since the overall bandwidth is so much higher with cable, the decrease usually isn't all that noticeable. Plus, since there are so many people who are now going with fiber optic, there are fewer people overall using cable, so there is less sharing of that connection. Overall, cable can provide a more robust service than DSL in today's implementations, but it might still cost you more. And again, neither cable nor DSL meet the performance of fiber, but that might be the most expensive option, or it might not even be available in your area yet. So when it comes to making a choice, it will simply come down to your needs, your budget, and which services are available to you. In this presentation, we'll compare and contrast various types of wireless internet access, beginning with what is thought of by most when the term wireless is used, which is of course what we refer to as Wi-Fi, which is short for wireless fidelity, which in itself borrows a term from audio, in that older stereo systems used to be referred to as hi-fis, which was short for high fidelity, but the official designation in terms of computing is IEEE 802.11, and the IEEE part stands for the Institute of Electrical and Electronics Engineers, and the 802.11 refers to a project that was initially undertaken in February, or the second month, of 1980. Hence, it became known as Project 802. And its goal was to define various standards for different methods of networking to eliminate the use of proprietary solutions that only worked with the equipment made by any given manufacturer. And at that time, 12 general standards or specifications were defined, including Ethernet, token ring, and fiber optics, and wireless networking methods were defined by Category 11. Hence, to this day, wireless networking is known as 802.11. Now, for most of us, that all simply boils down to the use of radio frequencies to carry data as opposed to physical wires that transmit and receive in the frequency bands of 2.4 gigahertz or 5 gigahertz. Now, just quickly with respect to each of those bands, 2.4 tends to carry the signal a little farther and can penetrate some obstructions more easily, but 5 gigahertz can carry more data and provide higher bandwidth. 2.4 also tends to be a little more susceptible to interference because there are other devices using that same range. So as long as you're within range with good quality signal strength, 5 gigahertz should be your first choice these days, but if your wireless access point is perhaps in the basement and you're on the second floor, then 2.4 might work better. Now, both of those frequencies, in fact, do not refer to the exact frequency of their namesakes. In other words, there are multiple and more specific channels within each band. And in the case of the 2.4 band, in North America, there are 11 channels, where channel 1 begins at 2.412 gigahertz, and channel 11 begins at 2.472, which allows you to possibly mitigate interference by setting the access point and your connecting devices to a different channel. For example, you and your neighbor might both be using the 2.4 band on the same channel, and you may be well within range of each other, so it's possible that interference is causing some issues with your connections. So if you try switching to a different channel, you might be able to eliminate those problems. The 5 gigahertz band uses channels as well, in fact, many more of them, and each channel is wider than it is in the 2.4 band. But since fewer devices use this band in the first place, and it doesn't carry as far as the 2.4 band, it's usually not necessary to reconfigure the channel being used. Cellular networks, of course, provide us with the connectivity for our mobile phones, and in the absence of Wi-Fi, these days they also provide us with access to the internet. Now, while internet access has been available over cellular service for quite some time, it wasn't until the advent of smartphones that it really came into being. Our individual devices connect to the closest cell towers, each of which still has a limited range in terms of coverage, but a reliable transmission range is known as a cell, hence the term cellular. But neighboring cells will usually overlap to ensure adequate coverage. But each will use different frequencies to avoid interfering with each other. In short, as long as you're within range of a tower, your service should be available, and you should be able to make voice calls and have access to the internet. Fixed wireless internet is a method used to provide broadband internet access by using radio signals instead of physical wired connections. Now, I realize that based on that description, that doesn't sound any different than Wi-Fi, but it differs in that it refers to the means by which the internet service provider gets the initial service to us in the first place. To clarify, of course, I do have Wi-Fi here in my home, but that primary service coming into my home from the internet service provider comes in over a fiber optic cable. So Wi-Fi is just a means for me to share that connection within my home with the other devices I have. But some locations might not have any type of wired connection available between them and the service provider, in which case the provider can send the primary signal to the required location using towers or ground stations at their location to transmit to the subscriber, where they will also install specific receivers. So where the entire connection in my case is wired from the provider, then wireless in my home, a fixed wireless connection would be wireless from the provider and wireless in my home. So this type of service can be useful for when subscribers are a little more rural or remote and wired infrastructure simply doesn't exist. Lastly, satellite internet is typically used by those with few or no other viable options in terms of gaining internet access, usually due to the lack of any other type of existing infrastructure, or in the case of extremely remote or isolated locations, such as ships out at sea or drilling platforms, or just very remote land-based locations such as research stations. As the name indicates, signals are transmitted via satellite, which are, of course, capable of reaching anywhere on Earth, making them a good solution for those isolated locations. Now, there are always pros and cons and various other considerations when it comes to choosing your connection options, and in many cases, such as satellite, there might only be a single option. But in any case, common considerations should include the price, the availability of the service, its speed and latency, and any data caps placed on your subscription that could result in overage charges. Just as a quick example with respect to the pros and cons, the main pro of something like satellite is global access, but its main con would be cost and latency. Satellites are obviously very expensive to implement, so that cost is passed on to consumers. And because they're so far away, there is always high latency with satellite, so it will usually come down to what you need versus what you're able to afford. In this presentation, we'll examine the basic storage characteristic of volatile versus non-volatile and the common implementations of each. So, beginning with volatile, this is simply any kind of memory that requires power for the data within that memory to be retained. In other words, if power is lost, the data is lost. Now, that might not seem like a very attractive feature, but in fact, volatile storage is used in a variety of computing components. Most notable among those components is the RAM, or random access memory, of our computers. And this has been the case really since personal computers came into being. And the primary reason for this is that volatile memory is much faster than traditional non-volatile storage, and the information that is contained within memory is usually only a working copy of what is already stored on the hard drive or the primary storage device. So your memory doesn't need to store anything permanently. Now, just for context, there are some caveats to that statement. For example, when you first boot your computer, of course, your operating system loads, and we see its interface. Well, all of the files necessary to load the operating system are stored permanently on the hard drive. But in order for the processor to interact with them, the necessary files have to be loaded into memory. But once that occurs, we can now work normally, and then once we're done, we just shut down, and all of those files are retained on the hard drive for next time. So again, we don't need any secondary copies stored permanently in the RAM. They just need to be loaded into RAM. However, for something like a document that you're creating for the first time, while you're typing away, the information in fact is only stored in RAM until you save it. Now, just quickly, these days most applications have autosave features to ensure that documents are saved regularly. But back when I began my career in IT, that was not the case. So if I spent an hour working away on a new spreadsheet, let's say, and I forgot to periodically save it, then someone tripped over the power cord and killed my power, all of that work was lost. So this is in fact the reason why autosave was implemented, because those types of situations happened far more often than we would have liked for one reason or another. But the key point is that saving the document ensures that it is written to non-volatile storage. And autosave just ensures that even if you do lose power, you would only lose the changes since the last autosave increment and not the entire file. But again, once it is saved, then we don't need to save it again in memory. So memory only acts as the temporary workspace that allows us to make changes. But in order for those changes to be retained, we have to make sure that we save them to the primary storage device. As for the increased speed, that was simply due to the fact that memory just uses electronic chips with no moving parts that can be addressed by the processor over a dedicated communications bus, whereas hard drives used spinning magnetic disks, so locating data on that disk was much slower than locating it in memory. Now, these days we have solid-state drives which also do not have any moving parts, but the nature of volatile versus non-volatile and other factors still make RAM, or non-volatile, faster to access. With respect to just RAM, there are two types, both of which are still volatile, but using different methods. The first is known as dynamic RAM, or DRAM, which uses small capacitors to store data. But capacitors only retain their electrical charge very briefly. Therefore, the power being fed to dynamic RAM must be constantly refreshed, which effectively decreases their performance and increases their power consumption. Conversely, static RAM, or SRAM, primarily uses transistors that can retain data as long as a steady stream of power is present, meaning that no constant refreshes are required. As such, static RAM does outperform dynamic in terms of pure access speed, but it also requires more space to store the same amount of data as compared to dynamic, plus static has always been more expensive than dynamic. So it boils down to static RAM is better suited to small, high-performance caches, such as those that are built directly into the CPU, which is typically only measured in megabytes. And dynamic RAM is better suited to the standard system memory, which these days can be many gigabytes. So non-volatile storage then, as you might imagine, does not require power for data to be retained. Now, there are many devices these days that require some form of permanent data storage, but the most common example in terms of personal computing is the hard drive, or the primary storage device of your computer. Now, the term hard drive does have a specific context because these days, of course, solid-state drives are far more common, but both of those devices serve the same purpose, which is to act as the primary storage device of the computer. But a hard disk is distinguishable by the fact that it uses solid metal disks that are also magnetic and can store an electrical charge. The disks are mounted on a central spindle and they rotate, while an actuator arm positions a read-write head over the appropriate area of the disk to apply the charge when writing or sense it when reading. That process of reading and writing is also known as mechanically addressed because of those moving parts. Solid-state drives, however, are similar to RAM chips in that they have no moving parts. Hence, data is programmed into a specific address within the circuitry, which is known as electronic addressing. This read-write process is also used in flash drives, and since there are no moving parts, both solid-state drives and flash drives can significantly outperform hard disk drives. But hard drives are still quite commonly used because they cost less, and there are some applications of data storage where performance simply isn't the main concern, such as backups or archiving data, in which case the cheaper storage of hard disk drives can result in significant savings for an organization. So when it comes to determining which type of storage to use, you should consider what it will be used for, what kind of performance is required, and of course any budgetary concerns. Now, just to finish up, for most of us at home, if a new purchase is being considered, such as a laptop or a desktop, then I certainly recommend going with a solid-state drive as your primary storage device. A single drive isn't that much more in terms of cost, although it will likely also have a smaller capacity. For example, and I'm just tossing out arbitrary numbers here as examples, so be sure to price these out yourself, but if a 1 terabyte solid-state drive is around $350, then that same 1 terabyte in a hard drive might be only half that price. Or, if you were to spend that same $350 on a hard drive, you might get twice as much capacity. But the performance gains of a solid-state drive are, in my opinion, most certainly worth the extra cost. Then, if you need additional storage just for backups or archive data that is only ever accessed occasionally, then something like a secondary hard disk would likely be adequate. In this video, we'll examine several considerations with respect to the most common types of local storage, including RAM, hard drives and solid-state drives, flash drives, and optical drives. So, beginning with RAM, the primary consideration for most of us is simply how much should there be? And in short, there is no specific answer in that regard, other than to say that it's better to have too much as opposed to not enough. But again, how much is enough? Well, it simply comes down to what your computer is going to be used for, and there are certainly some general guidelines. Now, it's somewhat obvious to state that memory-intensive applications will likely require your computer to have more memory, but which applications are more memory-intensive than others? Again, there's no single answer, but as far as home use is concerned, among the most demanding applications are games. Now, in that regard, I'm not referring to things like solitaire or various word games. Rather, the very graphic and/or very visually complex multi-user games such as first-person shooters and sporting simulators. In a workplace environment, special use systems such as those that run complex hardware devices such as medical equipment, or those used by graphics designers, 3D animators, or engineers or architects would also have much higher requirements than those that are only used for office-type applications such as word processors and spreadsheets, web browsing, and email. For those types of systems, it's quite likely that the amount of memory installed by the vendor is adequate, but you would often have the option to upgrade the amount of memory or to at least purchase the same or a similar model with more memory already installed. Now, some systems, particularly laptops, might not have the ability to be upgraded due to the physical space limitations, but in that case, it would likely already have the maximum amount that can be supported by that system. Now, there is another option known as virtual memory, which is actually a process that has been in use for a very long time, but it involves dedicating some of the available space of the hard drive or your solid-state drive to be used in the same manner as RAM. Since that space comes from the hard drive, however, it is slower than actual RAM, but it's dedicated and reserved for that purpose, so it can help to boost performance to a degree. Now, just quickly, I mentioned that this process has been around for quite some time, and it has, and in fact, it's actually still implemented by default in most cases. For example, on a Windows-based computer, the operating system will automatically allocate a certain percentage of disk space based on the amount of physical memory that is installed to act as virtual memory, even if your system has enough actual memory installed. It will still use the virtual memory to temporarily swap data out of RAM if it hasn't been accessed in a while. This just helps to ensure that there is always enough room in the actual memory for new data, and if that swapped out data is needed, it can be easily and quickly retrieved since it resides in that dedicated location. But ultimately, if your system is relying on virtual memory all the time, then that's an indication that you don't have enough actual memory installed. So a permanent solution would not be to increase the amount of virtual memory, it would be to get more actual memory. Hard disk drive considerations will typically include the revolutions per minute, or RPM rate, with a faster RPM rate value obviously translating into higher performance, but of course they also cost more. The typical RPM rate of a desktop hard drive is 7,200 and 5,400 for laptops. Higher rates are available for both, but again, they'll cost more. So for many, the more pressing concern is simply the capacity or how much data it can store. Typical values these days are in the low terabyte range, but just to put that into context, when I started my career in IT, the first systems I supported had hard drives of about 100 megabytes. Even just a 100 gigabyte drive is 1,000 times as much space as that, and a 1 terabyte drive would be 10 times larger than 100 gigabytes. So a 1 terabyte hard drive has 10,000 times the capacity of those old 100 megabyte drives. Now these days, solid-state drives are rapidly becoming the preferred choice for many, at least as their primary storage device, most notably because solid-state drives just use collections of memory chips, and as such they have no moving parts, whereas traditional hard disk drives have spinning platters and an actuator arm for the read-write head. Hence, hard disk drives are significantly slower than solid-state drives, but perhaps not surprisingly, solid-state drives are more expensive than hard disk drives. And for the same amount of money, you would get a smaller solid-state drive as compared to a hard disk drive. Now, that will vary by make and model, but in general, I would estimate that you could easily find a hard disk drive that is at least twice the capacity of a solid-state drive for the same price. That said, for just a single drive as the primary storage device of any given computer, you're likely only looking at a difference of maybe $150 to $300 more for the solid-state drive, depending on the size you need. Another non-volatile storage type is the flash drive, also known as thumb drives or just USB drives. And these have been in use for quite some time for a variety of storage needs, and since they just plug into any available USB port, they're also very compatible and can be used even across different types of systems depending on the file system used. And while flash drives use essentially the same type of storage as solid-state drives, they're physically smaller compared to even an external solid-state drive, and generally have less capacity, but they typically aren't used for any kind of primary storage. Their most notable characteristic is their portability and ease of use. The nickname thumb drive came about because most flash drives are about the size of your thumb, so they fit easily into any pocket or computer case. Lastly, optical drives also provide non-volatile storage by using lasers to read and write data to disks such as CDs, DVDs, and Blu-ray discs. Now, desktop systems might still often include some kind of optical drive, but many modern laptops don't include them any longer, most notably to facilitate smaller and lighter units, but also because one of their primary uses was to watch movies or TV shows from DVD or Blu-ray. But streaming services such as Netflix have, of course, largely replaced the need for having an optical disc installed. If you do have one, then DVD and Blu-ray remain the most common types of optical drives, although it wouldn't be out of the question to encounter an older system that only supports CDs, but modern optical drives can usually support multiple formats, so you don't need one for each type. Now, for things like movies or audio CDs, of course, the content is already written to the disk, so all we have to do is read it. But we can also write our own data to blank disks as long as the drives are writable, which has typically been referred to as burning because the laser is used to alter the temperature of the material, which physically alters its chemical state. So one state can be used to represent a 1, and another state can be used to represent a 0. And the only thing required to alter that state one way or the other is to vary the intensity of the laser. Original CDs and DVDs used, and in fact still use, a red laser, but Blu-ray derives its name from the fact that it uses a blue laser. And this is because blue light has a shorter wavelength than red, so it's essentially able to be more precise when writing, hence it's able to store more data on the same size disk. And when dealing with visual information, more data translates into higher resolution, which is why Blu-ray has become the preferred method for movies and games. Ultimately, if you need to store data without power, then some form of non-volatile storage is required, but the method you choose simply comes down to what you need to store, what kind of performance you need, and of course what it costs. But with the options available in today's market, there is almost certainly an appropriate solution for any need. In this video, we'll provide an overview of network storage types and cloud storage services, both of which provide methods for managing the ever-growing demand for storage in a networked environment. Now, to begin, when it comes to network storage, there are two basic categories with respect to how data is managed, known as block-level storage and file-level storage. Now, I'll actually begin with the latter because file-level storage is essentially what you and I deal with every day whenever we use our own personal computers, in that we have a standard primary storage device such as a hard drive. We create files and we save them on our local drives. But while that might be a very familiar process, there is in fact more to it because the hard drives we use have to be formatted with what's known as a file system. And with that, more than just the file is saved. The files we create also have attributes or properties such as who created it, when it was created, and what permissions exist on that file that might allow or prevent other users from accessing it. That information is also sometimes referred to as metadata, which can be thought of as data about data. The file itself is the core data, and those properties provide more information about that core data. In addition, whenever we do store a file, we always place it into some kind of hierarchical folder structure such as storing photos in the My Pictures folder, and even if you store it directly on the C drive, that's still considered to be the root folder of the system, under which all other folders reside. So, file-level storage simply uses that same type of structure, not just on your own computer, rather on network storage devices, which we'll come to in just a moment. Block storage, however, does not use that same file system, nor does it use hierarchical folders, nor does it store any metadata. With block storage, the total amount of space across all storage devices is aggregated, then broken down into collections of address blocks. And as data is written, it will simply fill up one block, then move to the next, and keep repeating that until the data is fully stored. Think of address blocks like a community post office box. We each have our own box, and our mail is simply delivered to our specific box, but other mail in other boxes is kept separate from ours. Block storage alleviates the management of attributes and file formats from the storage devices themselves because they aren't formatted with a file system like local hard drives are. The management of that metadata does still happen, but it's done by the servers that access and maintain the data and the subsequent applications they use. A commonly used example of block storage is for large databases. All management of the database files is performed by the server that hosts the database, through the database application and its associated services, but the core data itself just needs to be written to and read from the appropriate blocks of storage. As for the storage itself, it's usually in the form of a storage area network, which is quite literally just a large collection of storage devices, but no individual device has any kind of file system. They're all just aggregated together into one very large storage space, then again, broken down into addresses that represent the areas that will contain any given chunk of data. Many servers can then access that same storage over the network by simply referencing the addresses, just like we only go to our mailbox in the community mailbox. As for the choice of which to use, it generally comes down to the type of data being stored. Standard documents, such as those that we all use daily that do have attributes, such as file types and various other attributes, would typically be stored using file-level storage. These types of files are also generally referred to as unstructured because if you just sit down to write a memo, there is nothing that really dictates how that data should be organized. You just start writing. Block storage is more commonly used for structured data, and databases are a good example of that because when you store data in a database, you don't just sit down and arbitrarily start writing anything you want. For instance, if you're entering a new customer, there are specific pieces of information that must be recorded, such as their name, address, phone number, email address, and many others. Certain values might be required, while others are optional, and there might be restrictions on which data can be entered. For example, entering something like a state or a province might require a two-letter abbreviation. In short, there are rules that define the structure of that data. Now, file servers then are the systems within a networked environment that provide us with access to the data they manage. They're typically dedicated to performing network file management, although depending on the demands on that server, they can perform other tasks. For example, it's not uncommon for file servers to also be print servers, but that's up to the network administrators. But as their name indicates, their primary task is to serve up files to other computers on the network, typically the clients that work with those files. But this approach greatly simplifies storage, sharing, and security because individual copies of those files are not stored separately across many different client systems. There is only a single copy that resides only on that server that is managed and maintained by your network administrators. So for collaborative or Teams-based environments, everyone sees the same file, and changes by any given user are likewise seen by all other users so that you don't end up with many different versions that are scattered across many systems that would then need to somehow be synchronized with each other. Even if those files aren't being edited by any users, everyone with permission can still view and read the file. For example, a company policies and procedures document would not be something that would be edited by the day-to-day employees, so to speak. But by ensuring that there is only a single copy that can be viewed by all employees, then everyone knows the same set of rules, and unauthorized changes can't be made to that central copy. In addition, all the files on the file server would be protected with backups and/or replication mechanisms to ensure that data is always available and/or recoverable in the event of a disaster. So we as users don't have to worry about protecting the files ourselves. Other typical features of file servers include the ability to create and use a distributed file system, which I actually touched on a moment ago. A distributed file system means that data can be replicated from one server to another so that if the primary server fails, the same data can be accessed from secondary servers, which provides high availability for those files. Permissions management refers to the changes I also mentioned and whether any given user is allowed to make changes. Any file can have any set of permissions applied to any user or group so that those who should be able to make changes can, and those who shouldn't can't. And it's not just about changes either. It's the ability to even access the files in the first place. For example, HR-related files that contain personal information about all employees should only be viewable by authorized personnel in the Human Resources Department. Other employees shouldn't have access at all. And for those Teams-based environments that do collaborate on centralized files, conflict resolution mechanisms can ensure that changes made by multiple users don't conflict with each other, or a version history can be retained so that changes that are in conflict, or those that were simply made in error, can be discarded by reverting to an earlier version. And file locking can ensure that while one user is making changes, other users can't make changes until the file is saved and closed by the original user. Other users can likely view the file while those changes are being made, but they cannot edit it. As for the physical storage itself, with file servers, a common method is to use network attached storage, or NAS, which in itself is used to provide file-level storage as opposed to block-level. As mentioned earlier, block-level storage is commonly provided by storage area networks, which have some similarities to NAS in that the storage itself is not physically installed in the servers like the hard drives of our personal computers. It's typically in the form of a single unit that is connected to and accessed over the network. But storage area networks are essentially much larger and much more robust than NAS. For example, a NAS device might contain, let's say, 5 or 10 hard drives, whereas a SAN might contain hundreds or even thousands of drives. In addition, a NAS is typically accessed using the standard Ethernet network, so the device itself has an IP address, whereas SANs use dedicated types of networks with specific hardware and protocols designed purely for the purpose of accessing and managing large amounts of data. The servers that access the NAS device will use their inherent file-sharing protocols and permission management features to make the files available to other network users, while also providing that centralized storage that is easier for network administrators to manage and maintain. Now, to finish up, cloud storage also provides storage services much in the same way that network storage does, but the network isn't our network. It's the network of the cloud services provider. So we access the data by using the internet, or in some cases a dedicated private connection, but from our perspective as subscribers, the primary advantage is that we don't have to implement or manage anything in terms of physical infrastructure. That's entirely the responsibility of the provider. In addition, again from the perspective of any given customer, the amount of storage available to us is effectively unlimited. Although the more we use, the more we pay. But we can just keep storing as much as we need, and the provider will increase the physical components as needed. And they also ensure that high availability features are implemented so that we always have access to our data, even if servers or the entire data center goes down. As such, cloud storage is rapidly gaining popularity, particularly among business environments for its many benefits, including the ability to maintain business continuity throughout failures such as power outages or natural disasters, cost effectiveness because you only pay for what you use, And again, no physical infrastructure is required to be implemented on the subscriber side. Data management tasks such as replication and distribution can be implemented using inherent cloud-based features and services to create regional or even global delivery networks that place data as close as possible to those who consume it. As mentioned, you can scale virtually indefinitely, all without any concerns for infrastructure or the services to support it. You just keep adding data, and it can literally be implemented and deployed within minutes because everything is already in place at the provider. And it can be used to store just about any type of data, providing you with tremendous flexibility and agility with respect to creating new services and solutions. So, whether you need just a relatively small amount of data on your own network or thousands of petabytes available worldwide, with today's storage options, there is almost certainly one that can provide you with the solution you need. In this presentation, we'll take a look at the role and features of laptop computers, which in essence function exactly like any standard desktop computer in terms of the operating systems and applications they typically run, but of course they're designed to be entirely portable. Laptops, also commonly referred to as notebooks, come in a form factor known as clamshell due to the fact that they hinge along the back edge so that the display section folds up and the keyboard folds down. The name laptop clearly derives from the fact that you can work with the computer literally sitting on your lap if necessary, and notebook derives from the fact that it also opens much like a book, but these days the two terms are largely interchangeable. Typical features of laptops include a flat panel display that usually ranges from about 11 to 17 inches along the diagonal, and it's worth mentioning that laptops had flat panel displays long before they were the norm for desktop computers. And on that note, I would imagine that it's possible that some younger viewers may have never even seen a traditional CRT monitor, which stands for cathode ray tube. These were the standard monitors for desktop systems easily into the early 2000s, and they were as deep, if not more so, than the size of the screen. In other words, if you had a CRT monitor with a 21-inch display, it could easily be 21 inches deep as well, and rather heavy and awkward to move around. But by comparison to flat screens at the time, CRT monitors were much cheaper. Or to put it another way, earlier laptops were much more expensive than a comparable desktop, largely because of its flat screen. The keyboard is of course built into a laptop, and in almost all cases these days a pointing device as well, usually in the form of a touchpad, but both an external keyboard and mouse can be attached if desired, as there are still USB ports on almost any model. Most will have built-in speakers as well, and these days usually a webcam. And many models might also feature a touchscreen, but that's usually an optional component. As for power, since they're designed to be portable, laptops also include an internal battery that will usually run for several hours depending on the activity, but they also include a power adapter to recharge the battery, of course, but you can also run directly from the power supply, in which case the battery isn't used at all, which tends to result in the ability to configure what's known as power plans, whereby you can configure certain features to behave differently when running on battery versus when running off the power supply. For example, most systems will go into sleep mode automatically after a certain amount of time of inactivity. So in order to preserve the battery life, you can configure the system to enter sleep mode much more quickly when it's running on battery. You can also configure various applications to sacrifice some performance features in order to preserve battery life, or conversely, they can be configured to perform at maximum levels when plugged in. But if you rely on your battery often, then these various power-saving plans can help to get the most out of the laptop while running on battery. Now, one distinction that should be made is that laptops are not the same as tablets, although these days there are laptops that can be used like a tablet, in that the keyboard portion can be folded entirely back so that the system is effectively just the screen that can be used in a handheld manner by just using the touchscreen. But the general distinction is that laptops run the same operating systems as desktop computers, For example, a Windows-based laptop still runs something like Windows 10 or Windows 11, even if you're using it in tablet mode, and you can still also run desktop applications such as Microsoft Office. But a tablet such as an iPad does not run the same Mac OS found on something like a MacBook. While they are, of course, very compatible with each other, tablets run mobile operating systems such as iOS, which again is not the same as the full desktop operating system, so to speak. Tablets effectively sacrifice the ability to support desktop-level applications in favor of their even greater portability. That said, while they do run the same operating systems as desktop computers, due to their size limitations and space constraints, laptops tend to not be as powerful or as high-performing as desktop systems. And that's not to suggest that you can't get a high-performance laptop, but for the same money, a desktop system will almost certainly outperform its laptop counterpart. In other words, high-performance laptops will cost more. And again, this is simply due to the nature of the design. The form factor of every laptop puts a premium on space because in many cases, the smaller and lighter, the better. But that design also restricts airflow and minimizes the ability to keep components cool, which in turn requires them to run at lower performance levels. So again, if peak performance is required from your laptop, you'll very likely have to pay more. So to finish up, as for general pros and cons of each, on the pro side, desktop computers do tend to be more powerful, they're more expandable and or upgradable as well, and they can typically support many more peripheral devices as well, at least attached directly to the primary unit itself. They generally cost less compared to laptops, but of course the main con is that they're stationary. Laptops are effectively the exact opposite. They might not perform as well, they aren't as expandable or upgradable, and they're generally more expensive. But of course, you can take them with you wherever you go. So clearly a person who is on the move very often would benefit more from a laptop, but someone who wants a high-performing system that is only going to be used at home might do better with a desktop. Obviously, the choice is yours, so if you're considering a new purchase, then it will likely come down to the features you need versus your budget. So just be sure to do a bit of comparative research before purchasing. In this video, we'll outline the role and features of workstations, which are still generally desktop computers, but designed and built for high performance and or specialty tasks, often used for projects that are considered to be mission critical, such as software engineering, scientific research, financial analysis, and many others. Now, while workstations are often used for specific tasks or applications, the systems themselves offer a high degree of flexibility in what they can be used for because they're often very expandable in terms of resources and are powerful enough to support just about any workload. The physical form factor of a typical workstation is referred to as a tower, which simply refers to the fact that the case stands upright. Although the term desktop computer is used to describe most computers that aren't portable, more accurately, a desktop usually refers to a system that lays flat on its side. But in day-to-day conversation, the term desktop will often be used to describe just about any computer other than servers or laptops, but towers always stand upright. You might also see them implemented as rack-mounted units, although this is more commonly done with servers. But when you have more than one in use, rack-mounted units can save a lot of space because they house only the necessary computing components such as the storage, memory, and processing. Then, often a single monitor, keyboard, and mouse will be used in combination with a switching device so that a single set can be used for all rack-mounted systems. And while less common, there can still be workstations in the form of mobile devices such as laptops. It really just comes down to how that workstation needs to be used. Some more specific examples of applications where you might expect to see workstations in use include 2D and or 3D graphics, computer-aided design or CAD, commonly used in engineering and architecture, and artificial intelligence and or machine learning. Really though, the application itself doesn't matter all that much. Rather, it's the performance that matters. And again, the resources that are available in a workstation are usually fine-tuned to meet the specific demands of the dedicated task it's meant to perform. For example, most demanding workloads would put a premium on the processor and/or the memory, but they might not need a lot in terms of storage capacity. So the resources included tend to be a little more focused, but workstations are designed to be scalable as well to meet the ever-growing demands of today's services and applications. So if, for example, more storage is required, it can easily be added at any time. So in that regard, when it comes to some considerations for the resources, be sure to verify the processor requirements of the workload and/or to ensure that your system is upgradable with a faster processor if needed. And if the workstation is being used for graphics, engineering, or architectural design, then as much consideration should be given to the graphics processing unit. And for applications that implement intensive memory processes that require the most accurate data integrity measures, you might also want to consider what's known as error correction memory, which has the ability to detect errors in bit values within memory. As more and more data passes through the memory, heat can build up. That and other environmental factors have been known to spontaneously flip a bit value in memory from 1 to 0 and vice versa, which is detectable by error correction code memory to ensure that the data values that you're seeing are correct. Similar technologies also exist in other types of hardware, often referred to as RAS components, which stands for reliability, availability, and serviceability, which improves system availability and minimizes planned downtime and general maintenance, while also helping to ensure the integrity of your data. Ultimately, the typical characteristics that separate workstations from more standard desktop computers are the hardware and usually the dedicated applications or services they support. But they usually run the same operating systems and can support the same applications as any other system. So if you do have a more demanding or dedicated task that requires that extra bit of reliability and performance, then you should certainly consider implementing a workstation. In this presentation, we'll provide an overview of the role of servers in computing environments, which are still just computers, of course, but they often have significantly higher hardware resources, and they also run more specific versions of their operating systems. For example, for decades now, Microsoft has offered server-based versions of Windows that are different and distinct from their desktop counterparts, such as Windows 10 or Windows 11. They have a similar look and feel to the user, but they can host different applications than desktop versions and run services that just aren't supported on Windows 10 or 11. Regardless of the operating system, though, the defining feature of a server is in its name. They're designed to serve the requests of network clients. For example, when you click on Send and Receive in your email application, you're making a request of your email server to deliver your incoming mail and/or to send your outgoing mail, and the server will do as requested. On a day-to-day basis, servers are rarely used by anyone who is actually sitting at the console. They are certainly used when administrators need to perform various tasks, but most of the time, servers just respond to the many requests of client systems. So that type of request and respond computing is known as the client-server model of networking, and it simply refers to the fact that servers provide the services that we as clients need to do our jobs on a daily basis. We log into the environment each day. We send and receive email. We browse websites. We access central databases, work with documents, print them, and many other tasks. So in most environments, multiple servers are implemented, each with dedicated tasks to perform, or at least a few related tasks. But the number of servers required would come down to the number of clients they need to support, and/or the different types of applications and services that are required in any given environment. Some common examples of the services that servers can provide include file services, which host centralized copies of shared documents and/or the individual files of each user in the environment, database servers, DNS servers, which stands for Domain Name System, which is responsible for translating the names we use, such as www.myfavoritewebsite.com, into an IP address. Mail servers, print servers, web servers, application servers that host centralized copies of applications, proxy servers, which help to provide more secure web access by filtering which sites are allowed and which aren't, and even gaming servers for hosting multiplayer games. As mentioned earlier, another distinguishing characteristic of a server is the operating system that gets installed, which are designed with providing services in mind. And what that broadly means is that the resources that are available on those servers are fine-tuned to use those resources for what's known as back-end processing as opposed to front-end. And that really comes back to the client-server model. When we click on send and receive, for example, we're doing so from our email application that is installed locally on our computers. Or we might be using a web browser, but we're running an application that we see in front of us. Hence, it's known as a front-end application. But the server that processes our mail only needs to be running the email services. But those services do not require any interface to be up and running on the server, nor is any user required to be present. Hence, that service is referred to as a back-end process. However, in large organizations especially, it wouldn't just be me that is asking for mail to be processed, it's everyone in the entire organization. Now, of course, we don't all hit send and receive at the exact same time, but email is being sent and delivered all day, every day by just about every user. So the servers need a lot of resources to be able to handle that kind of workload. But those resources are not used in support of any front-end applications on the server. They're in support of the back-end processes. So while servers are very powerful overall, if you were to sit down at a server and run a front-end application, which can certainly still be done, it would likely not perform as well as it would on a desktop or a workstation, because those types of operating systems are tuned in the exact opposite manner to servers. Their resources are used in support of the front end, not the back end. Among the more commonly implemented server-based operating systems are Windows servers, which at the time of this recording is at version 22 for the year of 2022, and Unix and its variants known as Linux. Windows is a proprietary operating system of Microsoft, as is Unix, but there are different proprietary implementations, such as IBM's AIX or Oracle's Solaris. Linux, however, is what's known as open source, meaning that no one owns it, and it's actually free to use by anyone. It's designed and built by a community of developers and is very commonly used for services such as web servers, mail servers, and database servers. And overall, there might be a few more applications and services that can be supported on a Windows server as compared to Unix or Linux. But since most servers are dedicated to specific tasks, Linux can be a great option if budget is a concern because it's free. As for the location of any given server, that will depend on the organization, but as long as the client systems have network connectivity to the servers they need, then it's not terribly important where they're physically located, although I'll come back to that point in just a moment. But in short, there are three general locations. In-house servers means that they reside in the same physical network as the client systems who use them. These are also commonly referred to as on-premises servers. Larger organizations, however, may have many locations from which they operate, so physically distant servers might be accessible over a dedicated wide area network that is usually implemented through a telecommunications provider, or servers can be cloud-based, which in most cases means that they're accessed over the standard public internet, and the services they provide are paid for on a subscription basis, meaning that we as subscribers don't have to concern ourselves at all with implementing, managing, or maintaining the actual servers. We just pay for the services they provide. Cloud-based services are becoming more and more popular due to their ease of implementation and lack of any physical infrastructure needed by the subscribers. But coming back to the point of physical location, while a client device can access a server anywhere in the world as long as there is some kind of network connection between them, depending on the demands of the service being provided, location can certainly still matter. In short, a request made to a server that might reside in a room right next to your office can almost certainly be serviced more quickly than if that server is thousands of miles away and accessed over a WAN or the internet. But conversely, if that service needs to be accessed by clients all over the world, then cloud-based services are likely a better choice because providers can implement many instances of that service to ensure that global access is available. So the most appropriate location will usually come down to the type of service and where those who consume it are in relation to the server. But to finish up, you can implement any combination of any location. Many organizations these days will of course have in-house servers, but might also have WAN or cloud-based servers. It all depends on the needs of the organization, but no matter where they are, servers provide us with almost all of the services we've come to depend on to do our jobs. While they typically aren't found in home environments, we still make use of them every time we go online or send an email, and almost every workplace environment of even a modest size will need some kind of server to provide core business functionality to clients. In this video, we'll take a look at mobile phones and tablets, which of course have become ubiquitous in today's world of computing. And in fact, these days, so much is done on these devices in terms of computing that it can be easy to forget that they were introduced primarily as portable telephones, using standard radio frequencies to make calls over the cellular networks of telecommunications providers. Now, clearly all current mobile phones can still do that, but they've developed so much since their inception, and they can now support such a wide variety of other applications that making calls has become almost a secondary feature. On that note, mobile phones tend to be categorized now as either a feature phone or a smartphone, whereby a feature phone largely refers to older models that simply don't support the applications of modern smartphones. Hence, features such as calling and or text messaging are the primary features. But of course, there could still be some secondary features such as a calendar, reminders, notes, or even basic internet connectivity. But in short, beyond the primary features, functionality is limited. By contrast, smartphones can support applications that are often comparable to standard computers. Email, web browsing, video conferencing, and even line of business applications are supported by most smartphones, and as such, they've become the most commonly used mobile device, even for business workers. Among their capabilities are telephony, which of course is the service to support actual phone calls, text messaging, email, standard internet browsing, Bluetooth and near-field communication, satellite navigation or GPS, photography and video, standard applications, and gaming, all of which have contributed to the reason why they're now the most used mobile device. Now, while most of us in the technology world could more or less see this coming as mobile phones started to improve, for the younger viewers out there who might have only ever used a smartphone, I can tell you that the first mobile device that I owned didn't even support text messaging. You could make calls, keep contacts, and a basic calendar, but that was about it. Its screen was also maybe about 1.5 inches square. It was only a text-based menu system in terms of the interface, and it was monochrome in terms of color. So at that time, something like a modern iPhone or Android phone was almost unimaginable. Tablets, then, are certainly similar to mobile phones in that they are still handheld and very mobile, but depending on the make and model, they can generally be thought of as being somewhere between a PC and a smartphone in terms of functionality. Now, again, there's a fair bit of flexibility in that statement because it depends on the platform. For instance, Apple's iPhone and iPad are almost identical in terms of the apps they support and the interface, but most iPads don't include telephony services, although you can get that as an option. They do, however, all support Wi-Fi, so features such as voice or video calling are still available as long as you have network connectivity and all parties have compatible applications. Conversely, Microsoft's Surface Pro is a tablet that is every bit as functional as a full desktop computer, so while you might not be making calls with it, it would be much better suited to working in line of business applications such as spreadsheets, at least when compared to a smartphone, not only due to its increased resources, but the screen size alone makes it a much better choice for business applications because they're 4 to 5 times larger in most cases. So again, it will just come down to your needs. Now, that said, another consideration is in fact the operating system, which again depends on the platform, but for devices such as iPhones and iPads, they have distinct mobile operating systems installed. In Apple's case, it's iOS, and that's not the same operating system as Mac OS. So while tablets tend to have very similar functionality to their smartphone counterparts, they may not have the same functionality as the desktop or laptop counterparts. By comparison, however, Microsoft's Surface Pro runs Windows 10 or Windows 11, so the functionality is exactly the same as its desktop and laptop counterparts. So it's always important to consider the operating system. Android in particular, because it's based on Linux, which itself is open source, so many different vendors use the Android platform, including Google, Samsung, Sony, and many others. One characteristic shared by all smartphones and tablets these days, however, is that they are all battery-powered and touchscreen operated, so be sure to evaluate features such as the expected battery life when shopping for a new unit. In short, like most things, the choice of device will depend on your needs, but it's also very common these days for users to have several devices, in which case, if they're the same platform, then synchronization can be configured among them so that settings, apps, and data are consistent across all devices, which helps to ensure that you can keep track of all your tasks no matter which device you're using. In this presentation, we'll identify the role and features of gaming systems in the world of computing, which might seem a bit odd at first, mostly because a gaming system is really nothing more than a customized personal computer. But games have been a significant factor in driving the development of high-performance video due to the detailed nature of the graphics found in most games and the speed at which the on-screen image needs to be refreshed to accurately portray realistic movement along with the surrounding environment. So then, due to those performance requirements, most gaming systems will be custom assembled by the owners with particular attention paid to having a multi-core processor, a very high-end video card and graphics processing unit, and a significant amount of high-performance RAM, with the GPU being the primary point of focus in almost all cases. And just to give you a general idea of what that means in practical terms, it would not be uncommon at all for a gaming video card to cost as much or more than an entire desktop or laptop computer. In fact, if you were to just do a basic internet search right now for the top performing gaming video cards, you'd likely see prices well into the thousands of dollars. That said, the high-performing nature of gaming systems and their associated resources means that they're also very well suited to other tasks, such as 2D and 3D graphics animation, artificial intelligence and machine learning applications, and general high-performance computing jobs such as data analysis, all of which require resources similar to those found in gaming systems. So even in a business environment, you might find yourself working on what is essentially a gaming system. Now, similar to the gaming PC is the gaming console, and these are dedicated to running games, so they do have similar resources such as high-performance processing, video, and memory, but they don't run any kind of operating system that provides you with the ability to install other applications. For example, a gaming computer would have a standard operating system such as Windows 11 installed, and any other application supported by Windows could be installed. But gaming consoles only support the games that are designed for that console and platform. And there are typically no interface devices other than the proprietary controllers that come with the unit. In other words, there would generally not be a keyboard and a mouse like there would with a gaming PC. Now, that said, modern gaming consoles do support a limited range of apps. Because they're designed to interface with your TV or other type of monitor, apps such as Netflix and Spotify or other streaming services are available with most devices, and they also connect to your home internet, so new games and other software can usually be downloaded, although many games themselves are still run from optical discs such as DVDs or Blu-ray, and in that regard, they can also be used as standard players, so that you can watch movies or TV shows from those optical discs. So, like many other topics discussed in this course, the choice of a gaming console versus a gaming PC will come down to your specific needs. Gaming PCs can serve many other purposes, but they're larger and more expensive than consoles. However, if gaming is your primary concern and your budget is a bit limited, then a console might be ideal. One thing that is almost certain, however, is that games on either format will continue to drive the development of computing technology because consumers always want the most realistic experience, and manufacturers are always looking for that edge over their competitors. So, we can quite literally thank the gaming community for many advances in the world of technology. For our final video of this course, we'll provide an overview of what is known as the Internet of Things, or IoT for short, which is a rather broad term that can be used to describe any collection of physical computing devices that can communicate with each other over a network or the internet. Now, to clarify, my use of the term computing devices in this context does not refer to personal computers such as desktops, laptops, or even mobile devices such as smartphones and tablets. Rather, it refers to any device that is embedded with any kind of processor or microchip that is capable of gathering and/or exchanging information with any other such device. In more practical terms, one of the more commonly known applications of IoT, at least among the general public, would be a smart home, whereby certain appliances, security systems, thermostats, switches, and plugs can all be connected to a central controlling app or device. So if, for example, you're able to come home and tell Alexa to turn on the lights, then you are in fact using an implementation of IoT. Now, there are any number of consumer products available these days that support IoT. In fact, as of the time of this recording, the number of existing devices is estimated to be around 10 billion worldwide, and that number is expected to more than double in the next 3 years. But while a smart home might be a more familiar example of IoT for most of us, its industrial applications are seemingly unlimited. The amount of automation that can now be implemented using IoT, coupled with artificial intelligence and/or machine learning services, can help to create a much safer, consistent, and reliable workplace. And it can greatly improve productivity and quality as well. For example, in manufacturing, thousands of sensors and monitors can be implemented throughout the entire process to detect any kind of issue that might arise anywhere. And they can even predict when any given component might be likely to fail based on historical data, so organizations can work much more proactively as opposed to reactively. The driving factors behind the development of IoT include dramatic drops in prices for computing hardware in the last decade or more, coupled with the prevalence of mobile technologies. These days, almost any device with any kind of circuitry can work with IoT. On the software side, processes such as big data analysis and the cloud are driving its development just as much. Now, for those who might be unfamiliar, big data refers to the tremendous amount of information that is generated every day, particularly through social media sites and the general activities we all perform daily on the internet. For instance, if you use the internet regularly and you search for a particular type of product, let's say some type of sporting equipment, then you'll almost certainly notice that the ads you see in your social media feeds are now more focused on that sport, or at least vendors that sell those types of products. That's a direct result of analyzing a huge amount of data to determine that you're more likely to buy that piece of equipment or similar items. But given that volume of data, many organizations simply don't have the means to analyze it effectively. So this is where the cloud comes into play. Major cloud providers have almost unlimited resources at their disposal, so they offer the services to analyze that data on a subscription basis, so that organizations need only pay for the service, not the infrastructure required to implement that service in the first place, making it far more accessible to many organizations. But coming back to the world of IoT, that might be a little more familiar to most of us, typical devices include things such as televisions, home appliances, smart speakers, light switches and plugs, thermostats, security systems and IP cameras, streaming media devices, medical devices, our cars, fire alarms and smoke detectors, and fitness devices, any of which might be in use in your home right now. So even if you weren't familiar with what an IoT implementation might involve, you might already be using one. And as for the more industrial side, manufacturing, healthcare, transportation, automotive, retail, and the public sector, and many others have all been impacted by IoT, all to the point where, in fact, it's becoming standard, or is at least moving in that direction. So whether you make use of IoT technologies personally or not, there is undoubtedly some aspect of your life that is being affected by IoT, and as technology continues to grow and develop, we can expect to see even more aspects of daily life that are impacted in one way or another. So in this course, we've examined basic concepts surrounding internet access, storage, and types of computer systems. We did this by exploring fiber optic, cable, DSL and wireless internet, volatile versus non-volatile storage, local and local network storage, features and roles of laptops, workstations and servers, and mobile phones, tablets, gaming systems, and IoT. In our next course, we'll move on to explore basic concepts surrounding computer networking and wireless technologies.